Welcome to the Astrum Discovery Network, where we embark on a profound journey through time, space, and the origins of everything. For decades, humanity has visualized the beginning as a chaotic explosion, a sudden, violent burst of fire expanding into empty space. However, this popular image is fundamentally incorrect, because the Big Bang was not an explosion in space, but an expansion of space. Imagine the fabric of reality itself, stretching out, carrying galaxies along like dots on the surface of a rapidly inflating balloon. If we reverse the arrow of time, we see the cosmos contracting, becoming denser and hotter until everything merges together. Classical physics leads us to a singularity, a point of infinite density, where our current understanding of mathematics completely breaks down. Many scientists now believe the singularity is not a physical reality, but a sign that our theories are currently incomplete. Before we reach that impossible point, we encounter a chaotic epoch, where the fundamental forces of nature were likely unified. When we look up at the night sky today, we face a mystery that the standard Big Bang model cannot answer. The cosmic microwave background radiation shows us a universe that is incredibly uniform, with the same temperature in every direction. How could two opposite sides of the universe have the exact same temperature if they never had time to interact? This is known as the Horizon problem, a paradox that suggests the early universe must have been connected in some way. Another puzzle is the flatness problem, asking why the density of matter and energy is so perfectly balanced against expansion. Measurements indicate our universe is geometrically flat, meaning parallel lines stay parallel, which requires an incredibly precise initial density setup. In the late 20th century, physicist Guth proposed a radical solution to these paradoxes, known today as cosmic inflation. He suggested that in the first fraction of a second, the universe expanded exponentially, stretching faster than the speed of light. This theory posits that a region of space, smaller than a proton, expanded to the size of a grapefruit instantly. This rapid stretching smooths out any curvature or irregularities, solving the flatness problem by making the universe appear locally flat. It also solves the horizon problem, as everything was in contact for a brief moment before being ripped apart by inflation. The engine driving this expansion is a hypothetical energy field called the inflaton field, which permeated the early infant universe. As the inflaton field slowly rolled down its energy curve, it maintained a constant energy density, causing repulsive gravity. This repulsive gravity is what drove the exponential expansion, blowing up the fabric of space at unimaginable speeds for a moment. When inflation ended, the energy locked in the field was dumped into the universe, creating the hot soup of particles. This process, called reheating, is what we traditionally think of as the Big Bang, the birth of matter and radiation. Crucially, inflation took microscopic quantum fluctuations and stretched them to cosmic scales, creating the seeds for future galaxies. These tiny density variations became the blueprints for the stars and galaxies that make up our universe today. Without inflation, the universe would likely be a cold, empty, and twisted wasteland, incapable of supporting complex structures or life. Evidence from satellites like Planck supports the predictions of inflation, matching the statistical patterns of the microwave background perfectly. However, we are still searching for the smoking gun, primordial gravitational waves that would have been generated by such violent expansion. But if inflation happened once, the mathematics suggests a startling conclusion. It might never actually stop in the broader cosmos. This is the theory of eternal inflation, where the expansion continues forever in most places, stopping only in isolated pockets. Our universe becomes just one bubble in a vast, frothy cosmic ocean, surrounded by countless other isolated bubble universes. In this multiverse, each bubble could have different physical laws, different constants, and perhaps even different numbers of dimensions. This connects deeply with string theory, which posits that the fundamental constituents of reality are tiny, vibrating strings of energy. String theory requires extra dimensions of space, curled up so tightly that we cannot see them with our eyes. The way these strings vibrate determines the properties of the particles they create, forming the basis of all matter. There are an almost infinite number of ways these dimensions can curl up, each resulting in different physical laws. This creates a vast landscape of possibilities, suggesting that there is no single unique way for a universe to exist. This leads us to the anthropic principle. We observe these specific constants simply because we could not exist otherwise. In most other bubble universes, the laws of physics might prevent atoms from forming, leaving them cold, dark, and lifeless. We find ourselves in a rare, habitable pocket of the multiverse, not by design, but by the necessity of our existence. However, many physicists criticize the multiverse theory, arguing that if it predicts everything, it ultimately explains nothing at all. Since we can never interact with these other bubbles, the theory tests the very boundaries of what constitutes empirical science. Because of these difficulties, some cosmologists look for alternatives to inflation, seeking different origins for our cosmic history. One intriguing alternative is brane cosmology, which suggests our universe exists on a three-dimensional membrane, floating in higher dimensions. The ekpyrotic model proposes that the Big Bang was actually the result of a collision between two of these membranes. This collision could be a cyclic event, suggesting our universe goes through eternal cycles of birth, death, and rebirth. Nobel laureate Roger Penrose proposes conformal cyclic cosmology, where the heat death of one universe becomes the Big Bang of the next. In the distant future, when only radiation remains, scale becomes meaningless, setting the stage for a new Big Bang. Another contender is loop quantum gravity, which posits that space itself is made of discrete, quantized chunks or loops. This theory suggests a big bounce rather than a Big Bang, where a previous universe collapsed and then rebounded. Each of these theories offers a different narrative for our origins, yet all agree that the universe is evolving. With advanced instruments like the James Webb Space Telescope, we are peering closer than ever to the dawn of time. We are discovering galaxies that formed surprisingly early, challenging our models and forcing us to refine our understanding. Yet, we must remember that visible matter makes up only 5% of the cosmos. The rest remains a mystery. Dark energy is currently accelerating the expansion of the universe, mimicking a slower, milder version of the primordial inflation. Beyond the physics, we are left with the ultimate philosophical question: why is there something rather than nothing at all? Quantum mechanics teaches us that true nothingness is unstable. The vacuum is alive with potential and fleeting energy fluctuations. Do the laws of mathematics and physics exist independently of the universe, waiting to govern a reality that emerges? Some even speculate that the universe is mathematical in nature, or perhaps a simulation running on a higher substrate. Our journey from the center of the universe to a speck of dust in a multiverse teaches us profound humility. The future of cosmology lies in detecting the faint whispers of the first moments, hidden in gravitational waves and neutrinos. We are the universe experiencing itself, atoms formed in stars now contemplating the very process that created them. From the rapid expansion of inflation to the infinite possibilities of the multiverse, our origin story is grander than imagined. Thank you for joining this exploration on the Astrum Discovery Network. Keep looking up, for the answers are written in stars. Let us dig deeper into the mind of Alan Guth. His calculations in 1979 changed the course of modern cosmology. Standard Big Bang theory predicted an abundance of magnetic monopoles, heavy particles that we simply do not see in nature. Inflation solves this elegantly by diluting the density of monopoles, spreading them out so thin that we never encounter one. The concept relies on a false vacuum, a state of space that is unstable and holds immense potential energy. Like water freezing into ice, the phase transition from false to true vacuum releases the latent heat that fuels creation. The precision required for our universe to exist is often compared to balancing a pencil on its tip for eternity. In the strange physics of the early universe, high pressure actually creates repulsive gravity, driving the runaway expansion of space. Some physicists wonder if the Higgs field, responsible for mass, is related to the inflaton field that caused the expansion. The tiny quantum ripples, stretched by inflation, eventually collapsed under gravity to form the vast cosmic web we see today. Dark matter acted as the invisible scaffolding, gathering normal matter into the clumps that would ignite into the first stars. The first stars were massive giants, composed purely of hydrogen and helium, burning bright and dying young in violent supernovae. Their intense ultraviolet light burned through the neutral fog of the cosmos, bringing an end to the cosmic dark ages. Over billions of years, chaotic clumps of stars merged and evolved into the majestic spiral and elliptical galaxies we observe. At the heart of nearly every galaxy lies a supermassive black hole, anchoring the structure and influencing star formation rates. Unexpectedly, the expansion of the universe began to accelerate again 5 billion years ago, driven by the mysterious dark energy. If this acceleration continues, we face the big freeze, where galaxies drift apart and stars slowly burn out forever. Future civilizations might look up at a completely empty sky, unaware of the vast universe that once surrounded their home. This grim fate applies only to our bubble. Elsewhere in the multiverse, new universes might just be coming to life. The multiverse concept also appears in quantum mechanics as the many worlds interpretation, though this is different from cosmic inflation bubbles. Some physicists speculate whether the inflationary multiverse and the quantum many worlds are actually the same phenomenon, viewed differently. Our brains evolved to survive on the African savanna, not to comprehend 11-dimensional hyperspace or infinite parallel realities. Yet, through the language of mathematics, we can peer beyond our biological limitations and grasp the structure of the infinite. Giants like Stephen Hawking dedicated their lives to uniting the physics of the very large with the physics of the small. The holy grail of physics is a theory of everything, a single framework that unites gravity with quantum mechanics elegantly. Currently, our two best theories, general relativity and quantum mechanics, refuse to speak the same language at the deepest level. String theory is the leading candidate to bridge this gap, smoothing out the quantum jitters that plague gravity calculations. However, the mathematics of string theory is notoriously complex, offering 10 to the power of 500 possible solutions. Testing string theory directly would require a particle accelerator the size of a galaxy, making it currently impossible to prove. This lack of testability has led to frustration, with some asking if we have strayed from physics into metaphysics. Proponents argue that the mathematical elegance and internal consistency of the theory are strong indicators of its truth. Let us return to what we can see. Observational cosmology has transformed from philosophy to a precision science. We are currently facing the Hubble tension, where different methods of measuring the universe's expansion rate disagree significantly. This discrepancy might be a hint that our standard model of cosmology is missing a key ingredient or force. Neutrinos, ghostly particles that flood the cosmos, might hold clues to the asymmetry between matter and antimatter. The Big Bang should have created equal amounts of matter and antimatter, which would have annihilated each other completely. Somehow, a tiny imbalance allowed a fraction of matter to survive, forming the stars, galaxies, and eventually us. As the universe cooled, it underwent phase transitions, similar to water freezing, where fundamental forces separated from each other. The separation of the electromagnetic and weak nuclear forces was a critical moment that defined the chemistry of reality. In the first few minutes, the universe acted as a nuclear fusion reactor, creating the primordial abundance of light elements. The match between theoretical predictions and observed ratios of hydrogen and helium is one of cosmology's greatest triumphs. 380,000 years later, the universe cooled enough for atoms to form, allowing light to travel freely for the first time. This ancient light, stretched by expansion over billions of years, is what we detect today as the cosmic microwave background. It is essentially the baby picture of the universe, preserving the imprint of the cosmos when it was just born. Sound waves traveling through the early plasma left distinct ripples in the distribution of galaxies, known as baryon acoustic oscillations. These ripples provide a standard ruler for astronomers, allowing us to measure the expansion history of the universe precisely. Gravity amplified tiny initial differences over eons, pulling matter into filaments and leaving behind vast, empty cosmic voids. Some of these voids are hundreds of millions of light years across, regions of near total emptiness in the cosmic web. Our own galaxy is being pulled towards a mysterious gravitational anomaly known as the Great Attractor, hidden behind dust clouds. We reside in the Laniakea supercluster, a structure so immense it challenges our understanding of how gravity works on large scales. It is mind-bending to realize these largest structures in existence originated from subatomic jitters magnified by cosmic inflation. The specific arrangement of galaxies is the result of quantum randomness. Rewind the tape and the map looks completely different. While specific details are random, the statistical properties of the universe are predictable, confirming our theories of the early cosmos. Some theories suggest that inflation might have created primordial black holes, which could account for some of the dark matter. Astronomers are actively hunting for these ancient relics, which would offer a direct window into the chaos of inflation. Another mind-bending concept is the holographic principle, suggesting our 3D reality might be a projection from a 2D surface. This idea originated from black hole physics, implying that information is stored on the boundary rather than the volume. If true, it fundamentally changes our understanding of space, suggesting it is not a fundamental container, but an emergent property. Some theories even propose that time itself is an illusion, emerging from the entanglement of quantum states. The slogan ER equals EPR suggests that quantum entanglement is the thread that stitches the fabric of space-time together. This radical idea proposes that wormholes in space and quantum entanglement are actually two sides of the same coin. While these theories are captivating, we must ground ourselves in what we can observe, measure, and verify. We are limited by the observable universe, a sphere of visibility defined by the speed of light and cosmic age. Beyond this horizon, there is likely more universe, perhaps infinite, but its light has not yet had time to reach us. As expansion accelerates, distant galaxies are pushed beyond our horizon, disappearing from our view and causal contact forever. We live in a privileged time. Future astronomers will have less information about the cosmos than we do today. This realization drives our urgency to map, measure, and understand the universe now, while the evidence is still visible. Let's revisit the cyclic models. The idea of a universe with no beginning and no end has a deep philosophical appeal. The Steinhart-Turok model argues that the energy of the collision resets the universe, smoothing it out without needing inflation. It avoids the singularity problem and naturally incorporates dark energy as a force involved in the cyclic process. However, thermodynamics poses a challenge. Entropy always increases, making it difficult to build a truly eternal cycle. Roger Penrose suggests that when all mass disappears into radiation, the concept of scale and entropy might effectively reset. He claims we can see Hawking points in the cosmic microwave background, scars left by supermassive black holes from the previous eon. Most cosmologists remain skeptical, arguing that these patterns are likely statistical flukes rather than evidence of a past universe. Quantum cosmology attempts to treat the entire universe as a wave function, calculating the probability of it appearing from nothing. It suggests the universe could have quantum tunneled into existence from a state of absolute nothingness, spontaneously and without cause. Hawking and Hartle proposed the no-boundary proposal, where time behaves like space in the beginning, removing the start point. Just as there is nothing south of the South Pole, there was nothing before the Big Bang. The question becomes meaningless. In this view, the universe is completely self-contained, not created or destroyed. It simply is. Yet, this still leaves us wondering why the initial conditions were set to allow for such a rich evolution. Some fringe theories even suggest biocentrism, arguing that biological life and consciousness are central to the existence of reality. Drawing from quantum mechanics, they argue that the universe exists in a definite state only because we are here to observe it. Most physicists reject this, asserting the universe existed for billions of years before any consciousness arose to witness it. The flow of time itself is dictated by entropy, the tendency of order to dissolve into disorder. For time to flow, the universe must have started in a state of exceptionally low entropy, highly ordered and precise. Explaining this initial low entropy state is one of the biggest challenges. It is like finding a perfectly wound clock. Inflation offers an explanation. The massive expansion naturally drives the universe into a smooth, low entropy state. In an eternal universe, statistical fluctuations might create a fully formed brain out of the void, known as a Boltzmann brain. If the universe lasts forever, these freak observers should outnumber us. So why do we find ourselves in a normal evolution? This paradox suggests our understanding of the long-term future or probability in the multiverse is still flawed. If our vacuum is merely metastable, a quantum event could trigger a collapse that wipes out physics as we know it. This possibility of vacuum decay reminds us that the solid ground of reality might be more fragile than it appears. Despite these existential risks, the human drive to understand our place in the cosmos remains unstoppable. Cosmology unifies humanity. It is a collective effort to read the autobiography of the universe, written in light. We now build entire virtual universes inside supercomputers, testing our theories by recreating the cosmic history in silicon. The fact that these simulations closely match our observations gives us confidence that we are on the right track. Yet, puzzles remain, such as the missing lithium, which appears in lower quantities in stars than our theories predict. The Hubble tension persists, a stubborn reminder that our model of the universe is likely an approximation, not the final truth. These cracks in the standard model are exactly where the light of new discovery will eventually shine through. Artificial intelligence is now joining the search, sifting through petabytes of data to find patterns invisible to the human eye. Future missions like LISA will listen to the gravitational hum of the universe, opening a new sense beyond sight. We are small, fleeting creatures, yet we possess the audacity to measure the infinite and comprehend the eternal. Why do we care about the Big Bang? Because understanding our origin is essential to understanding who we are. The iron in your blood and the calcium in your bones were forged in the explosive depths of ancient stars. As Carl Sagan famously said, we are a way for the cosmos to know itself. We are star stuff, pondering the stars. From a speck of energy to a web of galaxies, from primal chaos to consciousness, the story is miraculous. Inflation explains the bang, smoothing the canvas upon which the masterpiece of the universe would be painted. The multiverse suggests that our masterpiece might be just one in an endless gallery of different realities. String theory attempts to read the fundamental musical notes that orchestrate the symphony of forces and matter. Alternative theories remind us to keep an open mind, for the truth often surprises us with its strangeness. Perhaps we will never know the full truth, but the pursuit of knowledge is its own reward. We pass the torch of curiosity to the next generation, who will see further and clearer than we ever could. There is a beauty in the unknown, a driving force that compels us to explore the dark corners of reality. Science is not a book of facts, but a process of constant correction, refining our map of the territory. While science answers the how, it often leaves the why to philosophy and theology, in a dialogue of meaning. Are we alone? The silence of the cosmos is deafening, yet the chemistry of life seems universal. Perhaps the seeds of life are scattered throughout the universe, waiting for the right conditions to bloom. In an infinite multiverse, it is statistically inevitable that other eyes are gazing up at other stars right now. We have shouted our existence into the void, hoping that someone, somewhere, might be listening to our call. The Fermi paradox asks, if the universe is teeming with potential, why have we not seen any signs of them? Maybe there is a great filter, a challenge so difficult that few civilizations survive it to become spacefaring. This possibility makes our survival on Earth even more precious. We might be the only light in this galaxy. Ultimately, our destiny may lie in the stars, spreading the light of consciousness to other worlds. Physics tells us that distances are vast, but not impossible to cross if we can master energy and time. Perhaps the very energy that drove the Big Bang could one day be harnessed to drive our starships. Trillions of years from now, the last star will die, and the universe will fade into eternal darkness. What will remain of us? Only the faint radio waves and the artifacts we sent into the abyss. Some theories suggest advanced civilizations could create baby universes, escaping the death of their own. Life, death, and rebirth might be the fundamental cycle not just of biology, but of the cosmos itself. When you look in the mirror, you are looking at a collection of atoms that has existed for billions of years. We are not separate from the universe. We are an integral part of its unfolding story and evolution. So tonight, go outside and look up. Feel the gravity that anchors you and the light that touches your eyes. Remember that the space between you and the stars is stretching, carrying you away into the future. The universe is vast, but the human imagination is vast enough to contain it all within a thought. We have traveled from the singularity that wasn't, through the fire of inflation, to the structure of galaxies. We have explored the bubbles of the multiverse and the vibrating strings that might compose the fabric of reality. We have looked forward to the end of time and back to the quantum origins of our existence. The story is far from over. Every answer we find spawns 10 new questions, and that is the adventure. Join the debate, share your thoughts, and continue this exploration with us in the comments and community discussions. If you enjoyed this deep dive into the cosmos, please subscribe to Astrum Discovery Network for more journeys. Check out our other videos where we explore the mysteries of black holes and the weirdness of quantum mechanics. This production was made possible by a team of researchers, writers, and artists dedicated to scientific accuracy. A special thank you to our supporters who make these complex visualizations and detailed scripts possible for everyone. We leave you with the breathtaking beauty of the pillars of creation, a stellar nursery sculpting new solar systems, the elegance of Saturn's rings, a reminder of the order that gravity can impose upon chaos, the fury of our sun, the engine of life, burning faithfully for 4.5 billion years, our neighbor Andromeda, racing towards us for a cosmic dance that will reshape our night sky forever. Light is the messenger of the universe, carrying the secrets of the past into the eyes of the present. Darkness is not just an absence, but a canvas, a stage for the grandest play ever performed. We are born of explorers, and our journey into the mysteries of the cosmos has only just begun. One day, we may call other planets home, but we will always look back at Earth as our origin. In the silence of space, we find the answers to the noise of our existence. Take a moment to breathe and realize that you are breathing the same air that dinosaurs once breathed. Matter is never lost, only changed. We are part of an eternal cycle of cosmic recycling. As we pull back, the Earth becomes a dot, the Sun a star, and the galaxy a smudge. We are woven into this web, connected to every galaxy by the invisible threads of gravity and history. And just as it began with a point of light, so too shall our story pause here. This has been a production of the Astrum Discovery Network, dedicated to the curious minds of the world. All content is researched and produced to bring the wonders of the universe to your screen. Let the music of the spheres accompany you as you return to your daily life, inspired and awestruck. Thank you for watching this journey on Astrum Discovery Network. Keep looking up, for the answers are written in stars.